Listen, firstly, thanks very much for inviting me to speak. We're not exactly 100 miles away, but given Mr. Drayford's announcements today, we might as well be 100 miles away. I call this talk The Science of Armageddon, not in light of the last 12 months or so. It's a little bit odd talking about global catastrophes when we're in the middle of one, but this is one that hopefully is rare, not likely to happen, hopefully within our lifetimes, but of course which is inevitable sooner or later. It's also quite a new subject. It's new because we made a mistake. That mistake dates back to Isaac Newton and before. He told us that the universe was, or the solar system in particular, and the universe in general, was a fairly quiet, predictable sort of place governed by the laws of gravity. You could predict exactly where everything was going to be thousands, even millions of years ahead of time. Also, this was a fairly unchanging system. It had existed for millions of years and will continue to do so. However, it wasn't long, just 150 odd years before people like Hutton, Lyell, Darwin showed up, who said that actually things do change, albeit over very long periods of time, evolution, biological, geological, and so on. And then we went into space and we had a close look at the other planets in the solar system. For example, we've got Mercury covered in holes. Venus, the same. If we go the other way out to Mars, we find exactly the same. Once we get beyond Mars, though, of course, we're into the realms of the gas giants, and you certainly wouldn't expect that sort of thing on a big ball of gas. But you'll remember, hopefully fairly clearly, back in July '94, we actually saw something, or bits of something, hit Jupiter, leaving behind very visible and very large scars on the upper atmosphere. That's not the last time we've seen this sort of thing happen. Back in August of 2019, we saw a body hit Jupiter, the flash, at about 8 o'clock there. And we've seen half a dozen of these impacts on Jupiter since Shoemaker-Levy 9 in '94. But if you look at the moons of the gas giants, which of course are solid, then we're really back to where we were. This is one of Jupiter's moons, Callisto. If you go out to Saturn, we've got Mimas. In fact, the thing that made the crater there was almost big enough to smash the moon to bits. This one got away with it. If you go out to Uranus, though, Miranda, this moon was smashed to bits. And later on, the bits then reaccreted to reform the body. Rather badly put together jigsaw puzzle. Even out as far as Neptune, you'll still find moons that are covered in holes. This is Proteus, one of Neptune's moons. You could go out as far as the minor planet Pluto, and again, we find craters everywhere. Where we don't immediately see loads and loads of craters, of course, is here on the Earth. But in recent years, we've found out that, of course, the Earth is actually covered in craters. We've got plenty of them, and more are being discovered every year. The real giveaway for all of this, of course, though, is the moon. Not only do we have a very intense cratering record on the moon, but we're also still seeing things that hit. This is the plot of things that have been picked up by the American search program that actually watch the moon to see if they can see flashes from the surface impacts. This all raises a question. What's doing the damage, and is there anything that we can do about it? And really, to get to grips with that, we have to go back to the beginnings of the solar system and see where all this stuff came from. As you'll well know, the sun was formed when a clump of gas and dust, it was mainly hydrogen gas, began to collapse under the force of gravity. Eventually, the core of this collapse got so hot and the pressure was so high, nuclear fusion could kick in and the sun ignited. But around that new star was a disk of dust, gas, and over time the dust began to accrete into discrete bodies that we now know as the planets. We ended up with 8 of them, small rocky terrestrial planets close to the sun and gas giants further out. But in between those two groups, the terrestrial planets and the gas giants, is a region where there should have been another planet. It didn't accrete into a planet because of the gravitational effects of Jupiter. Not only the tug as it goes round the sun, but the fact that Jupiter and the other gas giants oscillated towards and then away from the sun over a period of time. That collection of rocky debris is known as the asteroid belt, bits of a planet that never happened. They're rocky, metallic, carbonaceous to some degree, some of them. And we also now believe that there's a considerable amount of water in the form of ice and in hydrated minerals. There's quite a lot of these things. This is a recent plot from the Armagh Observatory. The green dots are all in the main asteroid belt. The ones in red and yellow actually have orbits that cross the Earth's or are likely to cross the Earth's within the next 100 years or so. So lots and lots of bits of rock and metal to deal with. Now we have another reservoir of material that could potentially collide with planets further out than the planetary region. We come to an area where ice, dust was too thin to actually form major planets. So we come to what's called the Kuiper Belt, a region full of these dusty, icy bodies. And further out from the Kuiper Belt, we come to the Oort cloud, which is a bubble of this material right round the whole solar system. These dirty snowballs or icy mud balls, depending on which way you flow, obviously, as you know, are known as comets. Most people seem to think comets look something like that. Actually, of course, that's much more what a comet looks like. But when that icy body begins to move towards the sun, for whatever reason, then the ices begin to sublime and release dust and gas, which forms jets, as the Rosetta spacecraft saw on its target. And that material then begins to form clouds, the coma surrounding the whole comet. When all of that gets even closer to the sun, then the solar wind begins to blow that cloud away. And that's what forms the famous tail of the comet. Now, little bits of these things, comets and asteroids, hit the Earth all the time. In fact, we pick up 100, maybe 150 tons of material from space every day. Most of that's dust. You'll all have seen meteors, shooting stars. These are normally somewhere between the size of a grain of sand and a grain of rice. But every now and again, we get something that's slightly bigger, something that makes it deep into the atmosphere before it's disrupted, these so-called airbursts. Now, if an object detonates in the atmosphere, it's going to create a shockwave, an intense shockwave that has the potential to do significant damage. We saw that back in 1908, when a little lump of asteroid, or more probably comet, somewhere between 50 and 60 meters across, detonated over the taiga in Siberia at an altitude of about 10 kilometers. Now, the yield of the explosion was somewhere between 15 and 20 megatons. That is an order of, well, a number of orders of magnitude bigger than the Hiroshima bomb. The damage on the ground was significant. In fact, an area the size of Greater London was completely destroyed. Luckily, no known fatal casualties. I'll stick a map of London up. I know it's not particularly relevant to Hereford, but I assume that most of you have been there, so you get the idea of the scale of the area that was damaged. Just over 100 years after that, in February 2013, we had a very strange day. On the 15th of Feb, everybody in the near-Earth object community was all hyped up for the close approach of quite a large asteroid called 2012 DA14. This was to occur at about 7 in the evening. But early in the morning, shortly after sunrise, my phone began to ring saying, this is the Daily Mirror, the Sun, or tell us all about this asteroid strike. Answer, A, it hasn't struck, and B, it's not due until 7 o'clock this evening. No, they said, the one that's just hit Russia. Now, you'll all be familiar with the Chelyabinsk event, purely coincidentally happening on that day. This again was a very small object. It was only about 17 meters across when it entered the atmosphere and detonated at about 20-30 kilometers altitude. A fairly small explosion, but there was some structural damage in the city. The main problem here, though, was glass. In fact, there were about 1,400 significant casualties that were hospitalized because of flying glass. These things aren't that uncommon. It's uncommon to have one close to a populated area, but the United States Air Force, along with others now, are plotting these things. This is the latest plot. I know it's only December 2020, but we haven't had any others since then. So these airburst events are not that uncommon. What is more uncommon is if we get something slightly bigger. Now, if we go up to an object about 150 meters in size, this will hit the ground. And when it hits the ground, it's going to blow a crater. Now, that's going to cause significant damage, the initial effects, heat, blast, and so on in the immediate area, but also will cause effects of dust being blown into the atmosphere, causing climatic change, perhaps for a couple of months, on the level of a hemisphere. Bigger ones, of course, well, they have much more dire effects. If we have a look at the sorts of things I'm talking about, our 50-meter object will be an airburst, which will destroy the area of a large city. Luckily, of course, not a lot of the planet at the moment is covered by cities. If you go up to that 150-meter, the initial effect will take out the size of a small country, Belgium, Holland, something along those lines. If we go a little bit bigger to the 1 kilometer sized object, then we're looking at a global problem, not from the initial effects, but from the amount of material that's blown up into the atmosphere. The dust will obscure the sun for a period of time, could be a few months, could be a few years, but that will cause the food chain to begin to collapse from the bottom upwards. Other material re-entering the atmosphere globally will ignite brush fires, forest fires, and that sort of thing over the entire planet. Bigger than that, then we're into the game of mass extinctions. It's reckoned at the moment that the threshold for a major mass extinction event will be an impactor somewhere in the region of 5 kilometers across. But luckily, these events are pretty rare. Now, we're fairly sure of that because we have the moon, where we can count and very roughly date the craters. We can date them basically by which ones overlap which. And using data like that, we can come up with a graph of impact frequency. Now, before anybody switches off, this is the only graph I've got, so no panic there, I hope. On this, you can see the relationship between the size of the impactor and how often we expect to get them. So, for example, our 10-kilometer size causing a mass extinction event, we would expect every few tens of millions of years. If we go down to the 1-kilometer size, the one that has global effects, we're looking at every few tens, possibly hundreds of thousands of years. If we go down to the Tunguska size events, then we're looking every few decades. So we do have a problem here. It's a natural hazard. It's along the same lines as earthquakes, volcanoes, tsunamis, but it is different in a couple of very major ways. Firstly, it's very, very rare. As we've just seen, these events are uncommon. That's a good thing. Or is it? In a way, it's not a terribly good thing, because if people haven't seen it on the BBC News, it doesn't happen. It's rare, but if it does, well, when it happens, it can be totally devastating, orders of magnitude worse than any other natural hazard that we know of. But the other thing that makes this problem slightly different to the others is that it's avoidable. We have the knowledge, we have the technology to make this problem go away. Now, that can't be said for things like earthquakes, volcanoes, tsunamis, and so on. So this is an instance where action can prevent the disaster. And to make it go away, we have a number of steps. Now, the first step is to find any objects in space, asteroids or comets, that have the potential to hit the Earth. Back in the late 1990s, the US Congress tasked NASA with finding 90% of near-Earth objects bigger than 1 kilometer across. To do that, they set up a network of existing telescopes to search for potentially dangerous objects. This is the LINEA program in Socorro, New Mexico. We've got Spacewatch in southern Arizona on Kitt Peak, the Catalina Sky Survey, certainly one of the most productive, and more recently, Pan-STARRS and its twin, Pan-STARRS 2, which is actually on the same site, but two telescopes can cover twice the amount of sky. Now, using telescopes like this, NASA's achieved that goal. The discovery statistics at the moment stand at just over 24,500 near-Earth objects have been discovered, 900 plus of which are that 1 kilometer size or bigger. So best estimate as at today is that we've hit about 96% of all the potentially dangerous asteroids bigger than a kilometer across. Now the search is moving to the smaller objects, and NASA's been told to find objects bigger than that 140 meter size. And really, to do that, we need a different generation of telescopes. For example, we've got the United States Air Force Space Surveillance Telescope, or SST, originally located in Arizona. It's now, sorry, New Mexico, and has now been shifted to the west coast of Australia. The European Space Agency are developing a network of so-called fly-eye telescopes. These are incredibly wide field of view instruments, enabling one of these to cover the entire sky in 2 observing nights. The aim is to have a network of at least 4 of these, 2 in the northern hemisphere, 2 in the south. But the real game changer in this game is going to be this one. Used to be called, well, it's still called the LSST, the Large Synoptic Survey Telescope, part of the new Vera Rubin Observatory. For those of you with aperture fever, that's the primary mirror, while just before it was polished. Now, the LSST will cover the entire sky down to magnitude 24 plus every 3 days. Now, on those images, we should find an enormous number of small moving objects, the asteroids. The data stream from this is 14 terabytes per night. That's where the problem comes in. We're not quite sure how the pipeline is going to handle it. But the fact is, we have the tools to do the job. We also have assets in space. You might recognize the Wide Field Infrared Survey Explorer, or WISE. Once it had finished its primary task, it was retasked to look for asteroids, the so-called NEO-WISE project. Absolutely ideal, space-based system looking in the near infrared. Asteroids tend to be quite dark in color, so they're hard to see optically. But where they shine is in the infrared. The problem is that for a decent IR telescope, it needs to be above the atmosphere. The atmosphere blocks off the infrared. So NEO-WISE was really the precursor to a new generation of search instruments. It's now finished its task. It's no longer functional, but we're hoping that very soon, like within the next 3 years, it'll be replaced by what used to be called NeoCam. Nobody's quite sure what it's called at the moment, but it's just got its phase 3 go ahead, so they can start to build the hardware. This is another IR telescope, very wide field of view, and it won't be in orbit around the Earth. It'll be at one of the Lagrange points between the Sun and the Earth. Finding them, though, is only the first part of the problem. Next, we need to know what they're like. What are asteroids and comets made of? How are they put together? Are they solid? Have they got cracks in them? Are they just flying rubble piles? And to a large extent, the only way of finding that out is to actually go there and have a look. And over the last 25 years, we've had a whole series of spacecraft visiting small solar system objects, asteroids and comets mainly. You'll remember that recently we've had the Hayabusa 2 touchdown, which actually picked up bits of comet Ryugu and has brought them back. Rather more successfully, one has to say, than Hayabusa 1. We've also had the touchdown of OSIRIS-REx, the American spacecraft, which again will be bringing back samples of asteroid Bennu. So a lot of work's going in to finding out what the physical properties of these objects are. Next, though, is working out where an asteroid or comet is going. It's all very well to find one. It's all very well to know what it's made of. But if you don't know where it's going, the whole process grinds to a halt. And to find out where it's going, you have to track it over a period of time. You have to measure very precisely exactly where it is in the sky at any given time, at the process of astrometry. And these days, most of that astrometry is done by the amateur community. Makes sense. If you know where to look, things are easier to spot. So even telescopes down to about 10, even 8-inch can be useful. But the amateurs are the backbone of the tracking fraternity. The data they produce is sent to the Minor Planet Center in the United States, where it can then be used to calculate and refine the orbit of that particular object. If that orbit's coming a little bit too close to the Earth, then other systems kick in. Bigger telescopes are deployed to track even more accurately and so on. So we can find them, we can track them. The next question, of course, is what to do when we find one that's coming. And when we find one that's coming, we've got a number of options open to us. The first option is the politician's option. It's probably not going to happen on my watch, so I don't need to worry about it. So head in the sand and hope it all goes away. Not acceptable. The second option is to go for the sort of Hollywood approach. Let's try and blow the thing to pieces. Well, that's absolutely fine. It just depends how stupid you want to look afterwards. Because all you've done is turned a predictable cannonball into an unpredictable cluster bomb. You may not get that big hole in the ground, but you'll have hundreds of thousands of Tunguska-sized events dotted around the planet. What you end up with is something probably a lot worse than if you just left it alone. That leaves us with the third option, which is to simply turn a direct hit into a near miss. If you can change the course of the asteroid or comet, albeit by just a tiny little bit, you could make sure that that object and the Earth do not occupy the same bit of space at the same time. And there's a lot of work going on at the moment to work out exactly how you can do that. And that work, of course, depends very heavily on the physical properties studies that are being done at the moment by in situ spacecraft. For example, we've got the ENIO SHIELD project. This is a European project looking at different ways of actually deflecting an asteroid or comet. For example, they're looking at the kinetic energy project. You simply smack something into the side of the asteroid to try and push it out the way. In fact, we're going to be trying that in a couple of years' time when the American DART mission reaches its target. it's actually going to smack an impactor into the side of a very small asteroid, and we can then measure by how much its course is changed. Look out for the DART mission in 2022. There is another way, and that's to use a process called ablation. The idea here is to heat up one particular spot on the surface of the object. That spot will vaporize. The vapor jets outwards, acting rather like a little rocket motor, and that pushes the object off course. You can do that using reflected sunlight, as in this case, with a mirror or high-powered laser, whatever. But this would be a very efficient way of dealing with the problem. Even more efficient, to be honest, is the nuclear option. This is the same as ablation, but like that, rather than over a period of time. You detonate your device close to the surface, not on the surface, but it's the heat and the radiation from the detonation that actually produces the jetting that pushes the object off course. If you've got plenty of time, you can go for the elegant solution, and that's to use gravity. You simply park a spacecraft next to the asteroid and gently edge the spacecraft away. The mutual gravity between the two will drag the asteroid in the same direction, the so-called gravity tractor. All of these are fine, though. The only thing, of course, is that we haven't tried them yet. And if you haven't practiced it, you can't do it. I've mentioned the DART project in 2022. That'll have a look. In fact, it was originally a joint project between ESA and NASA. NASA would provide the DART while ESA provided the AIM, which would then observe the impact. That sadly is not going to happen. The ESA project won't get there now until about 6, maybe 7 years after the impact. But it can do good in situ measurements of the orbit, and it can have a look for the crater and see what sort of damage was done. But I think the main thing about that mission is it demonstrates there's now much more international involvement in this issue, the issue of near-Earth object impacts. 20 years ago, this was almost entirely an American project. Now we've got international interest. I've mentioned ESA. As far as ESA is concerned, it set up the Space Situational Awareness Project, which actually looks at 3 different subjects. That's space weather, space debris, and near-Earth objects. So ESA is now in the game. The United Nations is involved through Action Team 14, which made recommendations to the Security Council. And we now have a framework for international engagement. I say framework because it's still work in progress, but the Committee on the Peaceful Uses of Outer Space now very clearly has the central role to play in an international response to, let's face it, what's an international problem. So recognition and potential action is now well underway. So we can estimate the rate at which we get hit on the Earth by counting craters on the Moon and observing the numbers of near-Earth asteroids. We can find them, we can track them, and we can make them go away. But there are a couple of elephants in the room here. I showed you this graph earlier on, but what it doesn't explain or answer the question of is, are these impacts, as the rate of impacts, steady, or is it cyclical? Do they come in peaks and troughs? Until recently, we've always assumed that the rate is fairly constant. But now we've started to date craters on the Earth, it's now fairly clear that, in fact, it's not a constant impact rate, but these things come in bunches. It's like buses in London. You know, you can wait for hours and then 3 all come at once. Now, part of this is because we've also assumed that the current near-Earth asteroid population is pretty steady, maintained by the leakage of asteroids from the main asteroid belt. But it takes millions of years for an asteroid to drift from a fairly stable orbit in the main asteroid belt into an orbit that crosses the Earth's, a dangerous orbit. So you would expect that population of near-Earth objects not to change over that sort of time period, but it does. Also, that leakage can't possibly account for the number of asteroid impacts that we see on the ground. The rate at which the Earth has been hit, certainly in the last few millions of years, is about 10 times higher than you would expect if it was just pure leakage from the main asteroid belt. Also, we have no geological record of any airburst events like the Tunguska event. They leave no craters. So we have no real way of knowing what the rate of those airburst events are. I'll throw that picture in just purely gratuitously because I quite like it. One explanation that could solve this problem of numbers and periodicity could be things called centaurs. Now, this is an image of one of Saturn's moons, Phoebe, but we believe that it's actually a member of this centaur population. They're in fact comets from way out beyond Neptune, as we discussed, that reach the inner solar system, having been literally bounced around by the gravity of the giant planets. They behave initially like asteroids, but as they get closer to the sun, then we see cometary behavior kicking in. It's estimated that we've probably got about 44,000 of these centaurs in the solar system, with diameters bigger than that 1 kilometer size. Now, as I say, they tend to be perturbed from the Kuiper belt and become Neptune crossing. As soon as they do, they're then classed as centaurs, but their orbits tend to be chaotic. They change very, very rapidly as they make repeated close approaches to the larger planets, the gas giants and the ice giants. Some of them will be nudged into Jupiter crossing orbits, and from there they can then be deflected into the inner solar system. In fact, this is happening right now for this little fella here. This is what was originally classed as an asteroid, 2019 LD2, which is now, because of its activity, classified as a comet. Now, these centaurs will either collide with the sun eventually, or a planet, or in fact be thrown out into interstellar space. But comets are fragile things. They have a nasty habit of breaking up when they're heated up by the sun or put under any stress, gravitational or otherwise. We've seen it happen. We know that comets can fall apart. But the disintegration of a large comet in the inner solar system would produce a mass of dust and bigger bits that could bombard the inner planets for as long as a few tens of thousands of years. But if we accept that large comets can arrive sporadically, then disintegrate and produce increased bombardment episodes, then we have to accept that impact cratering should indeed be episodic, as we see. We can also look at the amount of dust in the inner solar system, and at the moment there's a lot more than we would expect. This would suggest that a large comet, perhaps 100, maybe more kilometers across, disintegrated in the inner solar system within the past few tens of thousands of years. The effects of running through the debris trail of a large comet would involve the dumping of millions of tons of fine dust into the upper atmosphere and the arrival of hundreds, perhaps thousands, of atomic bomb-sized bolides over the space of just a few hours. These could, of course, do enormous damage. But as for the dust, detailed modelling of dust loading in the atmosphere was done back in the days of the Cold War, nuclear winter, and so on. So we know pretty much what we could expect. The dusting would reduce the level of the sunlight to that possibly of just moonlight, resulting in global cooling and the destruction of most agriculture. Historically, such sudden dips in the climate, or cooling in the climate, have led to the collapse of civilizations because of drought, famine, and so on. In fact, two such collapses have been linked with cosmic events. The first is the Younger Dryas event, a sudden global cooling about 12,800 years ago, lasting for over 1,000 years, which led to the collapse of a number of primitive societies in Southwest Asia, North Africa, and a substantial decline of large animals or mammals in North America, Europe, Asia, and indeed Australia. Apart from the effects of the dust in the atmosphere, a swarm of fireballs, bolides, could start wildfires over a significant area on the Earth's surface. And at that Younger Dryas boundary in the geology, there's a huge amount of charcoal, soot, evidence of extensive burning. Then about 2350 BC, some of the very earliest civilizations throughout the Middle East, India, China, all collapsed simultaneously, apparently driven by cooling, drought, and the failure of agriculture. A number of scientists have been looking at this, and they found evidence for asteroid or comet impacts at that date, widely spread as Peru, Spain, Syria. Estimates of the duration of that cooling do vary from perhaps just a few decades to a couple of centuries. So the breakup of a large comet in the inner solar system could sporadically generate a large population of small, short-lived impact events. Further evidence from meteor and fireball studies, which are underway at the moment, indicate that the number of impactors with diameters of tens of meters may be about 10 times higher than our current estimates based on telescopic surveys and crater counts on the moon. So we do seem to have a bit of an issue with the number of smaller objects that pose a threat. By smaller, I'm looking at somewhere between 10 and perhaps 50, 60 meters in diameter. It might be worth pointing out that all three of the major 20th century impacts That's Tunguska, 1908, British Guiana in 22, and the Curacao River in Peru in 1930, all coincided with our passage through the debris streams left by comets. In fact, the odds of that happening by chance are about 1,000 to 1. So the arrival of a centaur in the inner solar system brings with it the risk of a mass of dust and smoke in the atmosphere, hundreds of times worse than after an all-out nuclear exchange. It also appears that such events happen at least 100 times more often than globally threatening asteroid impacts. Whether the calamities I've mentioned in 2350 BC and 12,800 years BP were in fact due to cometary debris is still ongoing research. So we can't for sure say that that's the case, but the weight of evidence is stacking up that way. But we really do need to look at this centaur population and get a much better understanding of the environmental consequences of running through a stream of cosmic dust and comet fragments. So we have, as I said at the beginning, not so long ago, a bit of an elephant in the room here. While the situation might appear to be under control, there's still quite a long way to go. So where do we come in the game, into the game? Well, as has been mentioned, and some of you have been up here, Space Guard Centre sits about halfway between you and Shrewsbury on the England-Wales border. We have a number of instruments up here to help out with what we do. We have a legacy telescope, a 13-inch apochromatic refractor, f10. Not much use for what we're actually doing, but it's great fun to play with. Our main working telescope at the moment is a 14-inch Schmidt-Cassegrain, robotic, used for astrometry, for tracking asteroids and comets. But we do have a slight problem. For example, that's a picture of the moon. The field of view of the 13-inch refractor is that big. The 14-inch has a much bigger field of view, but still not quite the size of the full moon. What we need, if we want to get into the search game, is something with a much wider field of view. Something rather like that, a 24-inch Schmidt camera. This one, if you use the full 6-inch glass photographic plate, has a field of view of 5 degrees. Now, that particular instrument was in Cambridge at the Institute of Astronomy, installed in 1950, used for wide field sky surveys. That's what most astronomers did in the 50s and 60s. They mapped the sky in ever increasing accuracy. A nice instrument, Grubb Parsons, in fact, ideal for what we want. And by chance, the Institute of Astronomy decided to decommission the instrument, and for various reasons, it was offered to us. I had a phone call. We have a 24-inch Schmidt camera. Do you want it? Answer, yes. Not quite realizing how big it was, the fact that it weighed 7.5 tons, no funding and nowhere to put it. However, we set up the project called DRAX. Nothing to do with the power station. All the projects here are named after James Bond villains. And to be honest, DRAX was the next on the list. With the help of a couple of local companies and lots of volunteers, we removed the instrument from its dome in Cambridge. An interesting project since nobody had actually done it before. and the fact that the right ascension ring on the mounting is actually wider than the slit in the dome. But all was well, loaded onto a truck and brought across the border into Knighton. Luckily, one of my volunteers, the chief engineer, owns a factory not so far away from here and gave us some space to literally put the telescope to sleep, while we then considered exactly what we were going to do with it and where we were going to put it. In fact, once it had been cleaned, all greased up, we shrink wrapped it and it sat waiting. We decided to put it here. You might be able to see on the paving stones some red paint. That's the outline of where we planned to put the dome. What we didn't have, of course, was any funding. So we saved up for a bit to get materials and so on, and then set the volunteers to work. Luckily, one of them's an architect. So he managed to design the dome for us, produced all the drawings and so on, and then we got going. We started building. We actually, before the building was complete, lifted the base assembly of the camera onto its concrete plinth in the dome. We had to do that before building or laying the upstairs floor, or at least the joists for the upstairs floor. To go on the top, we decided we needed a dome, so we built one, a 26-foot dome. We built them in fiberglass sections, 2 per week, 26 sections, and then we started to build the dome itself. Not without its setbacks. We are, at least one occasion, we trashed the whole thing in a storm, but it only took a weekend for the volunteers to put it all back together again. We lifted the optical tube onto its mounting in the building, closely followed by the dome itself, which I'm pleased to say is, after a year of neglect, still going round and round as it should. The telescope itself has been stripped of its mirror, the corrector plate at the front, and the camera mounting, but we're working at the moment on the electrical system. 1947 electrics are not particularly reliable in this day and age, so we've stripped all of those out and completely rehashed the system. So the electrical system is well underway, as is the mechanical system. We're trying to use as much of the original instrument as we possibly can. That includes the right ascension drive, which you can see here, with its 3 motors, giving us three speeds. That motor, I'm pleased to say, has now been completely stripped down, rebuilt, and is working. It's working fine. The work that isn't finished, not by any means, is the shutter mechanism. We built the shutter. We were about to install the mechanism when lockdown happened. During lockdown, some of the more mechanically minded, if you like, of the volunteers have completely redesigned the whole thing. We have most of the components fabricated now, and hopefully within the next month or so, we'll be able to install the shutter opening and closing mechanisms. But that, of course, all depends on our dear friend Boris. During lockdown, the dome itself, nothing's changed. I've been going in every day to make sure that everything is tickety-boo and still working. In fact, it's also been used as a film studio on at least one occasion during lockdown. One of the things we do have to change on the Schmidt camera is the detector. Nobody uses circular glass photographic plates anymore, so we're replacing the original detector with a rather nice CCD camera. We've recently had the mounting built for that. It should be fairly simple to install. Now, we won't get the full field of view out of that, of course. However, we will get a pretty good field of view, at least 2 degrees by 1.5, which actually makes this a pretty capable search system. I'm pleased to say that we've had a number of fairly high-profile supporters for this project, one of which I'll show you a picture from the I Love Me file. But of course, lockdown has taken its toll. We've been unable to work on the project now for just over 12 months. Hopefully, once we get going again, the momentum will pick up. We were going for an opening of Project DRAX at the end of June this year. Asteroid Day, International Asteroid Day, it's the 31st of June. It would also mark the 20th anniversary of the Space Guard Centre opening, but not to be, so we may have to go for the 21st anniversary. We shall see. But that's what we're up to. The problem hasn't gone away, though. We still have an issue with near-Earth objects. We've bagged most of the big ones, but we're still way, way behind when it comes to those smaller objects below 1,000 meters across, up to about 140. We probably only tapped about 15, maybe 20% of those. And once you get below the 140 meter mark, then we are probably decimal points of a percentage. So a long way to go, but at least we have an idea of how to do it. It's just a case of whether we want to. As I mentioned before, this is a problem that's rare. So it's not very well understood by the general public. It's certainly not understood by the politicians, who of course hold the purse strings here. In fact, when I briefed the Secretary of State a number of years ago, her first question was, is it going to happen before the next general election? When given the answer, no, you can see the shutters come down, don't care. But it's rare. You have to remember, though, that when it happens, boy, does it happen. In fact, it's the only natural hazard that we know of that puts the future of entire species at risk over a very short period of time. But as I said, it is avoidable. So really, my final word, my last question is, are we any smarter than the dinosaurs? They're extinct because they didn't have a space program. We can make the problem go away. It's not a case of we can't do it. It's a case of we can't be bothered to do it until the day comes. But at that point, I shall shut up and I pause.
Thanks, Jay. That was extremely interesting and very informative about not only what's been happening, but all the other projects that's undergoing at the moment. I was particularly interested in, you mentioned Neowise and the Pan stars, because the number of small comets that have been picked up by those particular things has been quite significant over the last few years. So that is very good as they possibly change them over the future. So over to you, Chris. Shall we open it up to everybody now to see if they want to raise any questions?
Yeah, I'm just asking everybody to unmute everybody.
I will stop sharing the screen now.
Thank you, Jay. Keep it handy though, because you may need to go back to one of your pictures. I don't know, but so feel free to unmute and pop a question either directly or in the chat if you want. Yeah, can I offer my thanks as well, Jay? That was wonderful, fantastic. I mean, it may be quite frightening, the consequences, but it is a great opportunity for spectacular pictures and photos, isn't it? They all look wonderful, but I wouldn't want to be underneath one of them. But yeah, wonderfully illustrated as well. Thank you. Does anyone have a question to start with, or shall I kick off the ball rolling like I normally do? Okay. Jay, what you mentioned, the Oort cloud, obviously the asteroid belt, you know, the usual sort of suspects, and the Kuiper belt, the Oort cloud. What about and mapping all this stuff? Now, obviously, there is always room for error. There is still a small percentage we might not know about, and there could be something else lurking that we haven't spotted. But even assuming we've got everything safely mapped, so far as the really large impactors are concerned, at least mapped out long enough into the future for us to do something about it, which I think is the objective, isn't it, really? What about true foreigners, you know, interstellar objects, like, for instance, not long ago we had Oumuamua, very strange thing, half comet, half rock, but that came from almost nowhere, but literally from beyond the solar system and beyond the Oort cloud, presumably, because it was interstellar. Is that a threat as well? I mean, I assume it is, but I mean, could it present a threat in the sense that we have less ability to see something like that because of its angle of approach, or it's going to be even quicker than the traditional sort of speeds we're looking at?
Well, the latest thought is that we would expect to see possibly half a dozen extra solar objects passing through the solar system every year. Now we know what to look for. I mean, we've already bagged another one. So yeah, they're a problem, but not what I would call a critical problem. It's all a matter of threat assessment. These things would come pretty low on that list. One thing they do or could do, though, is come from any direction. But that applies to comets as well, our own comets. If you look at the Oort cloud, it's a bubble right round the whole solar system. So the so-called long period comets, ones with periods of more than, well, officially more than 200 years, can literally come from anywhere. Most of the search programs are looking at the ecliptic plus or minus about 15 degrees. That's where you find the vast majority of asteroids and short period comets, the Kuiper belt and so on. The reason for that is quite simple. If you're being funded to run a search program, your funding depends on success. Therefore, you're going to look at the bit of sky where you're most likely to find something. And certainly most of the big search programs are quite upfront about that. It's not a big secret. What we're hoping to do with DRAX is look at the bits of sky that other people aren't looking at. We don't get any funding, so I don't have to impress anybody. So we don't have to have a constant stream of discoveries. Yeah. So we will be looking, I guess, banking on the fact the system works, which of course is no guarantee yet. We'll be looking at bits of sky where we'll be looking for the long period comets. But as far as extra solar objects are concerned, they are a threat. But a very small subset of a much larger threat.
Yeah. Okay, thank you. I have a question from Francis, who is one of our regular members, who is also a very keen and very able astrophotographer. Francis is being particularly shy, but Francis, do you want me to read the question on your behalf, or? I'll take that as a yes. He's can't hear him anyway. So what Francis wants to know about your Schmidt camera, saying it has a curved focal plane, or the Schmidt camera rather has a curved focal plane. Does your new camera, new to you that is, have a correction for the curved focal plane?
Excuse me, not yet. What we want to see, because it's a 6-inch plate, designed for a 6-inch plate, the glass plates were curved. Well, flat in the packet, but curved by the camera mounting. We've got a 35mm chip in the camera. Question, can we get away with that without a corrector lens? The answer is, well, the people I've talked to, both in the United States, Australia, and here, 75% of them say, yeah, you should be able to get away with that without a field corrector. 25% say, not sure, I'd want to try it. So what we're going to do is try it first. Then if we need a corrector lens, then we'll have to have one made. But I'm hoping not. I'm hoping not.
Okay, I hope that answers your question, Francis, because I feel like the pub quiz landlord who only knows how to pull a pint but knows nothing about general knowledge and asks a question that he doesn't understand the answer to, or even the question. But I hope that does some way to answering it for you. Anybody else? Anybody else got a question for Jay?
I was just wondering, Jay, did you see that Winscombe event recently, or?
Oh yeah, the Cheltenham thing.
No.
Yeah.
Our all sky camera picked it up, but we have two all sky cameras here. One's for me to check the weather, and the other is set up by University of Dundee, part of a global network. They picked it up on the camera here. We didn't see it because we're looking at a very small field of view, not in the same place. And since we operate the telescope remotely as a general rule, unfortunately, we weren't outside at the right time.
Yeah.
But I have a nice photograph of it from the all sky camera here.
Yeah, well, I was out observing that particular night. I didn't actually see the thing itself, but the time that was actually mentioned, I heard this terrible bang, and I didn't know what it was. I just assumed it was something in the area. I went indoors, and the wife said, "What was that bang?" And it was only later on that when I actually saw the timing it occurred, it was the same time that I heard the bang. So I can imagine that was loud enough. So some of these airbursts that you mentioned, I can imagine how catastrophic they must be, because that was quite a loud bang I heard.
Yeah, it was quite a loud bang. I mean, not the only one, of course. We've had a couple recently. More often than not, though, the bang might not be quite as big, but they tend to be masked by the normal noises of living. And half of these things, of course, happen in daylight. And if they're not really, really big, then you simply don't see them. So we miss an awful lot. Having said that, you're looking at very small objects here. Probably no bigger than a microwave or a fridge. So it's not that uncommon. What's uncommon is for people to notice it, if you see what I mean.
Yeah.
Nowadays, of course, after the last few weeks, anything that goes bang in the sky has to be a meteor, which it isn't, but there you go.
Have they been able to make some kind of extrapolations then, Jay, about the size of the object and the velocity? Because of by definition, it did hit the ground. It did make the ground. It wasn't big enough to, it wasn't an airburst. It was, and someone has actually found bits on their drive, haven't they? So can we kind of work some way towards estimating its size? You mentioned a fridge or a microwave. Is that based on some kind of calculation we can make, or?
The calculations made by the size of the explosion, well, the energy output from the explosion, and the calculated velocity, because of course the energy of the explosion is a function of the mass and the square of the velocity. It was fairly slow, that one, probably 12 to 15 kilometers per second, probably less than a meter across.
Okay.
And at that sort of velocity, because it was porous, it was a carbonaceous chondrite, you would expect fragments. What's unexpected is to actually find the fragments.
Yeah.
But if they land in the middle of your drive, it's a bit of a giveaway.
Yeah, yeah. In the middle of the
ones
woods
that land on the lawn or in the woods next door, or the sea, of course, you simply don't find.
No.
So, but that's a goodie. I mean, it's lovely to have fragments, and the Natural History Museum are actually over the moon. We've got a locally grown carbonaceous chondrite, which are quite rare, rare.
Yeah.
You know.
I have another question for you, Jay, this time from Neil Raha and Roz. How does the composition affect the consequences of an impact for any given size?
The composition will determine how far into the atmosphere it'll get, because of course the stress on any object entering the atmosphere is enormous because of the speed, the velocity. If a thing's fairly loosely bound, be it rocky or icy, then the chances of breakup on entry are much, much higher. That doesn't mean to say it's harmless by any manner of means, because you get lots of little bits, not one big bit. It's the one big bit that causes the crater to form. So you need something fairly strong going at moderate speed to form the crater. By moderate speed, 15 to 20 kilometers per second. So the composition of the object is important, but so are the physical properties. How is it put together? We now believe that the majority of asteroids are simply flying rubble piles, lots of little bits glued together by gravity. That reduces the hazard, because they will break up in the atmosphere much more easily.
Yeah.
Something big and solid, then you've got a bit of an issue. They're the ones that are going to hit the ground and blow a crater. The thing that happened at Meteor Crater in Arizona, for example, was probably almost exactly the same size as the Tunguska object, 40 to 50, maybe 60 meters across. But it was iron. So it hit the ground and it blew a small crater.
Mm.
So, you know, composition and how the things put together are two really quite important properties that we need to know about.
Yeah. I was looking at your website, and there's a good picture of you standing on the edge of Barringer Crater. You've obviously been there. So that must be almost a holy grail for you in some ways.
Not as much as Manicouagan in Canada.
Oh, right. Oh, yes. I've seen that on Google Earth. Yeah.
Yeah. Well, I was posted to Canada for 3 years, and we potted up to Manicouagan, very fine pub just on the edge.
Yeah.
And of course, Sudbury. Canada, the Canadian Shield is a marvelous place to look.
Yeah.
Ancient geology, not changed very much. Loads of craters, just like Australia.
Mm-hmm.
Except Australia, of course, is big, flat, it's a desert, and nobody lives there. So, good place to look. That's why Gene Shoemaker used to go there to Australia every year to look for craters.
Okay. Anyone else? If not, I've got one more on a more personal level, Jay, if you don't mind me asking. I wish you many, many more years of successful research, and in a funny kind of way, I hope you don't find what you're looking for, if you know what I mean, at least for our own safety. But in the longer term, you're almost a one-man show up there. I mean, what are the plans for the continuance of that station? And in the longer term, I'm not trying to get rid of you, please don't misunderstand me, but I mean, what provision is there in the longer term? Is there a kind of line of succession, if you like, or have you given that any thought, if you don't mind me asking?
I don't mind you asking in the slightest. I have no intention of being up here forever and ever.
No.
That will very largely depend on the views of the guy who actually owns this place. So I can't really speak for him. When it comes to the technical side, I don't have many fears for that. The team of volunteers that do all the work up here, mainly from MAG, the Marches Astronomy Group, they're going to go on for some time. So when it comes to keeping the instruments operating, that is not going to be an issue, I don't think.
Okay.
Who takes over when I decide enough's enough? That depends on the guy who actually owns the place.
Yeah. Yeah.
And obviously we haven't seen him for over a year. So
yeah.
I haven't managed to ask him, to be honest.
Okay. Well, I thought that was the last question, but if you don't mind, Jay, there is a couple more. Just briefly, are you okay for time?
Yep.
Paul Thornley asks, what about seismographs on the moon? Has this produced any evidence of impacts? I suppose he's thinking of the impact counting on the moon visually with the craters, etc. But you know, we've got seismographs up there, so does that contribute to the data?
Well, it did while they were still working, but yes.
Okay.
Absolutely. There were a couple of events where they picked up a whole cluster of events. That data is one of the reasons we began to then look at the smaller objects that certainly on the Earth don't leave any evidence, and why people started counting the flashes on the moon where things actually impact. So they certainly played a pivotal role in looking at the rate at which the moon is hit by small objects. And the latest development in that line, of course, are the images from LRO, the Lunar Reconnaissance Orbiter, which is picking up new craters simply by comparing new images of a patch of ground with old images of a patch of ground. And that data too is telling us that our rate of impact for smaller objects is actually much higher than we'd originally thought. So seismometers, good news, and the physical observation of the moon to look for these flashes, good news.
Okay. And finally, from John Theron, he asks, how many asteroids bounce off the atmosphere or of the Earth per year? I suppose he's thinking about not just a near miss, but one which is technically within the atmosphere, but still has sufficient velocity or angle of attack to actually be deflected by the Earth's atmosphere. Does that happen?
The great 1972 event. Yes, it certainly happens. The problem is we don't really have the ability to detect events like that, or we didn't have any ability to detect events like that unless they were, you know, really significant, until the Americans started their fireball program. So I can't put a number on it, to be honest, because if it doesn't hit the ground or it doesn't airburst, not my problem.
No.
But it'd be I'll have a look. It'll be interesting to find out.
Yeah.
But it certainly happens. We've seen it happen.
You mentioned 1972. What was that then? That was a...
the Grand Teton event.
Yeah.
it actually entered the atmosphere over New Mexico and basically flew the height of the United States before leaving the atmosphere again. In fact, it came back round only a couple of years back and missed by, I think, about 2.5 lunar distances.
Still pretty close in astronomical terms, isn't it? Yeah.
Well, a bit of a bullet burn, yeah.
Yeah.
But it was a fairly small object. It was probably no bigger than perhaps 100, maybe 150 meters.
Okay.
Other events have been detected by the American fireball detection systems, but I couldn't put a number on it.
Okay, Jay, I'm going to thank you, but we will thank you again in a moment. I'm going to hand back to Mark, and everybody else. Can I just ask you all to stay on with us for a minute, because we have yes, I'll hand back to Mark, but also don't go away, everybody. If you can just stay around for a few more minutes. Mark, back to you to thank Jay.
Okay, well, hopefully, Jay, one day the Society will be able to come and visit you again at Knighton, because each time we've been, it's been highly enjoyable. I'm sure that we would all like to have a trip out to see you. And could I ask everybody to show their normal appreciation by going into reactions and giving a clap?
A virtual clap.
Thanks.
Of all the times I've done this, I've not seen that before. That's really cool.
Yeah, well, it shows our total appreciation to you, Jay. It really is.
Yeah, no, it was great. Wonderful. Thank you very much.
Well, not a problem. It's been an absolute delight. And as I say, once we're back up and running, more than happy. But do remember, you're in England.
Yes,
we're in Wales.
Yeah, yeah.
The rules are different.
It all depends on Boris and Mark, doesn't it? Yeah.
Yeah.
Well, let's go with Mark, shall we?
Yes.
Yes, a good idea.
Not a problem. Listen, I am actually going to have to run.
That's fine.
Okay.
Thanks ever so much for listening, and hopefully we'll see you soon.
Lovely.
Okay, Jay.
Thank you again, Jay.
Okay, then.
Bye-bye. Take
Bye
care.
now.
Bye.
Right, I'm just stopping the recording.